In item 3, we have an indeterminate beam, and we're asked to find the reaction at A, but only the flexural reaction of the 3 that are there at this fixed end. We're given that we have constant EI, and normally when I see something like this, I'd immediately want to remove the prop out here and handle it in that kind of fashion. However, when you go to look at the beam tables that are available to us that have cantilever beams, we have a point load at the end, point load in the middle, an end moment, a distributed load all the way across that's uniform in its intensity versus a triangular or linearly varying distributed load. We don't have any that is only partially across. That's kind of a stinker. If we look at the simply supported beams that are available to us in our table, we have a point load in the middle, point load offset, end moment, and we have a full distributed load across the full beam and one that's partial, and then a triangular distributed load all across the entire beam. It's the fact that we have this case number 5 that will be useful to us, because we can break this up by removing the flexural reaction, right? So that's our first step. Remove M sub A, and we'll have then a simply supported beam with a distributed load that goes across 10 feet. And we can then let that thing deflect, and because we've removed MA, we have then allowed a rotation to happen, where in the original situation that rotation is supposed to be 0. Here it will not be 0 in the primary system. And we can go now and figure out what that is, and directly we can figure out what that is. Given to us direct right here. Notice theta 1 is the one that's on the left, so our theta A0 then would be equal to a minus W, that's 1.5 kip per feet. A is the distance from the left over to the end of the distributed load, that's 10 feet squared, 2 times our total span length of 14 feet, minus A of 10, and that whole quantity is squared, all over 24 times the L of 14 feet times EI. Again, when we go take a look at what that number is going to be, if we're smart, we won't put in all the numbers. We'll just kind of keep this somewhat symbolic. We'll have 100, that's the 10 squared, times the 1.5, times, in the bracket we get 28 minus 10, but that has to get squared, and then we'll divide by the 24, and we end up with a negative 2025 kip foot squared over 14 EI. I can bet that if we divide by 14, you just get an ugly real number. So I'm just going to leave it like that for now. Then we're going to come along and replace the redundant reaction. And so we'll impose a moment that will pop things in the other direction. That's our moment at A, and that will cause a frowny face curve like so, and we want to go figure out what that theta right there is due to our redundant reaction. And that is happily given to us right here. Notice now that this moment is opposite of what we want, so we want the opposite equation for that rotation of ml over 3ei. So theta am equal to a positive m sub a times L of 14 feet over 3ei. Right? And so that means now that we'll go to write our compatibility equation. That will use superposition here, and so theta A will equal theta AO plus theta AM. And we have a minus 2025 over 14 EI plus our M times 14 over 3 EI. And we know that that turns out to be 0 in the original structure. And so now we can let the EI's get canceled out. And the moment that we seek is going to be 3 times 2025 over 14 squared. We had kip feet squared here. There's a feet. That's a feet that goes in there too, I think. I can check units again, double check in just a moment. Oh, no, the 14 here no longer has units. We got kip feet squared there because we had, and then we got that feet that comes around. So we're going to get just a kip foot, which is what we should have. And 3 times 2025 divided by 14 squared equals 30.99, or an answer that M sub A is equal to, let's see, this was shown up in the positive sign convention. This would be a negative value for a negative moment there of 31.0 kip feet.